So z-scores are, when you output a z-score and you calculate it, we'll talk about how to do that in a second. It means the number of standard deviations away from the mean that you are. So if 50 is in your sample is 1.5 standard deviations away from the mean, that is, we are with a z-score outputting that 1.5 value. It'll make a little more sense in a second. So we are, as I said, fitting our non-normal data in some cases, or something that has a different standard deviation or a different mean. We're fitting it to that standard curve. That's what this is doing. And that's used for other things down the line, particularly confidence intervals. So I don't know if we'll get to that today, but this is used for that. And confidence intervals are pretty much one of the most important things that you can have. It's an error range. And you need this to calculate an error range. So as I said, all of the data points will have the same units in this case. And then when you have that standard normal curve, the area under the curve is always 1. And I explained this earlier, no matter what your units are, it's still going to be standardized to that normal distribution. So now get to calculating, and you're going to try this. So I have the code that is written here is in R. I'm going to explain this, and then I'm going to run it for you. And I'm hoping that you can use that information in order to try to replicate it with different data. I'm going to do a little refresher of a couple things in R before that. But so a z-score, say we have values of data or a prescribing rate. We saw our mean was 80. Well, what if I want to know how many standard deviations away 90, a prescribing rate of 90 is? So this measures how far away from the mean a value is in your data. So in order to calculate that, we have the value we're trying to test. So if we're trying to see how far away a value that equal to 90 is from the mean, that's what this is going to be. That's what value means. So that's what you're trying to test. You subtract the mean, and then you divide by the standard deviation, not the standard error. Standard error is used later for confidence intervals. So it's the value minus the mean over the standard deviation. So I gave an example down here. I made this as big as I possibly could, but if you can't read, you can look onto the slides. So here we have, and I use this example. So in this case, we're looking at what is the z-score of a prescribing rate of 70 in the opioid data set. So in order to do that, I found the mean prescribing rate in the opioid data set right here. If you want to output this to its own variable, you can. I wanted to show it in one spot. So that's what this is doing, the mean of the opioid prescribing rate. I recommend every time you use mean, standard deviation, quantile, any of those basic statistics, add na.rm equals true. If you have any missing values, if you ever see an NA come out of a mean function, it means you have missing values and they need to be removed. Almost every basic statistics function requires an na.rm equals true. So we're finding that mean value. We have 70, what we're trying to test. We subtract that mean value, and then we divide by the standard deviation of that same prescribing rate. And then it tells us here a negative 0.4. So that means when we look at this normal distribution, our value will be almost halfway between the middle value and the first standard deviation. If you're looking at it, it'll be on the left. So it's lower than the mean, the mean value in this case. So our mean would be a higher value. No, you'll get an NA.
Oh, okay. So it doesn't do.
No. So they do that, I'm sure, for a data check, so that you know it's not. If you outputted 0, you wouldn't know whether it was really 0 or not. But it's always NA. Same thing if you have infinite, so by dividing by 0 and null values. If you have them, you have to remove them, or you're going to get null or infinite, or it's going to error out. It's not going to work. So be mindful of that when you do data analysis, because it's not just simple like means. They screw up a lot of functions. So what I do before I do anything is I check for NA values, and you'll see in that code I did. I'm not having you write that part because you're not going to know how to do it, but you'll see the output. So Z-scores are used for confidence intervals for the most part, and then also for p-values, which we'll get to next week. Not sure if we'll get to confidence intervals or not. So confidence intervals are our error range. Every sample is going to have error in it because you're choosing randomly. That always means that there's going to be error. And that's what the standard error is measuring, is the error in our sample mean. If you're looking at the mean, will be the error in that sample mean value. So, and you can also, like I said, use it for outlier removals. I will talk about confidence intervals more later. So I'm going to go in, show you my example. And I broke it into smaller steps in the actual code, but I also wanted to show it in one string on the website, or on the PowerPoint. So I am going to go. I had you in all the examples. I have prescribing rates in here and overdose rates by county. I am going to say do it with overdose rates, and I'm going to have you do it with prescribing rates, or vice versa. So here, I wanted to show for everyone, and I coded everything that isn't simple. Everything else you can use as a math. So when I say randomly sampled the values, I put that in there for every example, and you already have that done for you. I'll show you in a minute. But this summary function I use a lot. So when you can see down here, what this outputs is the mean, median, minimum, 25th percentiles here, and the 75th percentiles here, the max. So that's just something to get a bird's eye view, and your Z-scores will make more sense when you can see that value. So I'm going to go here. And so we're going to calculate, and we're seeing that 70 is below this median value. So knowing that, our Z-score should be negative. So it would be, actually it's the mean, I apologize, I misspoke. So if it's below the mean, it should be negative. So if you get a positive number when you're looking at something that's below the mean, then you did something wrong. So as I said here, we have this mean value divided by the standard deviation. I mean, the value we're trying to test, which is 70, minus the mean value over the standard deviation. So I believe down here, yes. So this is actually the better example. Example of overdose rates. So like I said, the prescribing rates are a population, so you have to sample from them in order to get a random sample. So I did that. In practice, you wouldn't want to do that because it doesn't make sense. But so down here, this is actually where we should start. So I would start, okay, here. All right, I apologize. So here we have that 70 value, again, minus the mean over standard deviation. So I'm going to run that. We're seeing a negative 0.4. So that's what I showed in our PowerPoint. Now I'm going to try it with overdose rates. We're looking at 15 in this case. So if we look at the distribution here, we're seeing 0.2 is our minimum, our mean is 6.8, and our maximum is 43. Remember, I said there were a lot of large outliers. This shows that. So, and our NA values, this is another way to find NAs. There are 20 of them. So that's why we needed the NA.rm equals true in this case. So I'm actually going to show something because don't think I showed this example probably well enough, and I'll leave it up here. So when you code, you embed a whole bunch of pieces of code within one another, and I don't even think about it anymore, and it should have been done probably like this. So if we were going to do this, say we wanted to find the mean and overdose rate, NA.RM equals true. So now if we print that, it's 6.8. So now if we take the standard deviation of overdose, this is how I recommend doing it, probably, unless you understand the one that's done in one step. So we're going to do that standard deviation, and we're doing the same exact value, so we can copy and paste it into here. Have that, and I accidentally had an extra. So we have that standard deviation value. Our data is really spread out, so the standard deviation is pretty high. So now I recommend to do the z-score calculation of overdose for 15 value. I recommend doing it this way because this will make more sense to you. So we're looking at 15. Do 15 minus the mean dot overdose over standard deviation of overdose. So I recommend doing it that way because now you can see it in all of the steps, because I'm going to have you do it for different samples. So I did both overdoses and prescribing rates here. I'm going to leave this up on the screen so you can see it. So I would use that as your model, but I subsetted below the data to just the South region. It tends to be the worst off of all of the regions. It's overdose rates and prescribing rates tend to be higher in this region. And I also created that summary statistic here for you. That's already done. And then we're going to, I say what I want you to find the z-score of. It's going to be in that South data set, and I'll scroll back up so you can see the example. Just try to follow the pattern. One other thing that I want to go and look at real quick. So if you do the view, you can get rid of this ribbon. Okay. So just a real quick refresher. Most basic elements, when you see the caret and the hyphen, that means you're assigning to a variable. That's assigning a value to a variable. And then this $ is pulling a single variable out of a data set or a data frame. So it looks similar to a CSV. So in this case, we're going to be looking at in opioid.data frame. We're going to be looking at the prescribing.rate variable. So you'll see in all those cases, we have this. But up here, when I'm assigning the mean to this mean overdose, I use the assignment. So given that, I'm going to make this larger. There are 2 exercises in the comments down here. Try to do it yourself, and I'll go over the answers after you guys are done. And if you have a problem, please, and I'll come around. So I go up here. This is the example I recommend using. I did it, what's above is I did everything in one line of code because I wasn't thinking that it would probably, it's more complicated looking. So if you could get the code and try that yourself. So we have that opioid South subsetted data. So I asked you to find the z-score of 105. So as we would up here, so what you probably would have done would go up here. So first we have to find the mean prescribed South. Again, using formative names. So we're gonna find the mean of opioid South, and then we're gonna use the prescribing rate, and then NA.RM equals true. So hopefully you got 98.9. So almost 100 bottles were prescribed per 100 people in the South. So the next thing we're going to do, if we come up here, next thing is standard deviation. So standard deviation, prescribe dot south. So we use the standard deviation function, opioid south. We again do the prescribing rate, na.rm equals true. Okay, we run that, make sure it works. Our value is 23, so very, very spread out. Next thing we're gonna do, go up here, just look. So in this case, we're gonna have 105, so that'll go where this goes. And then we're gonna subtract the mean and divide by the standard deviation. So we have z-score south 105, and then we take, remember, order of operations. So sometimes I just tend to use parentheses in all cases, because in this case you definitely need to. But going back to what 7th grade algebra, but make sure you be mindful of that. So we are going to do 105 minus mean prescribed came up, and then we're going to divide by standard deviation prescribed south and run that. We can print it. Value should be 0.25, what you should have gotten. Okay, questions about that? And I can go on to the next one. Okay. So the next one we're going to do of the overdose rate. So we're going to do z-score south 20. Oh, whoops, getting ahead of myself. Okay, so mean dot overdose dot south. So we have the mean. We have again the opioid data frame. This case, we want the overdose rate, na.rm equals true. Then we go on to the standard deviation, overdose south. Always check for typos first when you get an error. You'll learn that. It's most of the time, it's something super simple that you're going to kick yourself for. So now we go down, run. And then we have we want to do 20 minus mean overdose south divided by, oops. And then we'll print that. Should have gotten 2.43. So that's, again, we're going to go up real quick, rerun this. So we go down here. So for the overdose rate, our mean is at 7.6. So it makes sense that our z-score is very high and positive, because that's way higher than the mean. Now, if we go up, our z-score for this was 0.25. So the prescribing rate that we're looking at is 105. So if we go down here, we see 105 is pretty close to the mean, and it's a little bit above it. So that means that the z-score is going to be small and not negative. So that's how you would check it. I think, putting this on here and not going through it step by step. I try to, when it's good, to go through step by step. Mm-hmm.
Are we using the opioid data set or the subset?
So yeah, the subset, it'll say that in the comments. So if you read the comments, it tells you what to do. Sorry, here.
Yeah.
Opioid.south. I apologize. Thank you.
Oh yeah.
Apologize. Okay, then that should 1.98. Is that?
Yeah.
Okay.
Yeah.
Good.
Okay. I was like, how did I mess this up?
Nope, it was me, and that's just how it is. Unfortunately, it happens. Go ahead.